Our next speaker is Raphael Cuevas. Dr. Cuevas is a research associate at Kentucky State University. He's going to talk about reuse technology opportunities for aquaculture and decommissioned wastewater treatment facilities for paddlefish fingerling culture.
Thank you. So I'm going to be talking about the opportunity of using decommissioned wastewater treatment facilities for paddlefish production. So the goal of the project is to develop a safe and sustainable water supply for aquaculture using reclaimed water. Reclaimed water, I'm going to put into context here the difference between sewage-fed aquaculture, wastewater aquaculture, and reclaimed water aquaculture. Sewage-fed aquaculture is one of the oldest techniques in aquaculture, where the sewage was directly dumped into a small reservoir. And from the production of the organic matter, fish were raised. Although sometimes fish cannot handle too much organic matter and is detrimental for the lake. The wastewater-fed aquaculture is going to be part of the treatment process. So fish are raised during different treatment of the process, and they rely on the nutrients on the water. And a good example of this is in India, in Calcutta. They have different series of lagoons or ponds, and they use wastewater to raise fish. But there is concern over contaminants that could have these fish being raised in this water. If we keep treating the water further, we can disinfect it, and we can take the waste out of the water. And this is what is called reclaimed water. It's a secondary treated, disinfected water that could be used for aquaculture. In fact, this water is even cleaner than the one that we take up down the river for drinking purposes. If we want to increase aquaculture in the United States, we need to find new sources of water. Why? Because as we see in this graph, the percentage of lakes and rivers in the United States are under some kind of advisory, meaning that some fish have contaminants in more or less 42% of the nation's total lake acres. And if we know that aquaculture used around 9 billion of gallons per day, this was in 2005, and 78% of this water comes from the surface water. So new water sources need to be found, and reclaimed water could be one option, because there is around 15,000 municipal wastewater treatment plants that produce 33 billion of gallons a day of reclaimed water. And this water is just dumped into a river and never reused again. So it's just a waste of resource. And now, with a stricter regulation that EPA has and the increase on water consumption, new wastewater treatment facilities has been built. But what happened with the old facilities? The old facilities, they have tanks that could be easily converted for aquaculture purposes. And also, we can use the water that is the reclaimed water for aquaculture and retrofit it back to the main treatment process. So it's a big circle, zero exchange. We don't really use water because we are just borrowing for the new wastewater treatment plants for the aquaculture production. And we can produce fish out of this water. The second phase on this research is a high population of Dania during the treatment process. In the secondary clarification, there is a lot of Dania that has been easily harvested and used to raise larvae. So what we have here? We have free water, it's clean. We have already existed tanks. We have free food. So this means business. And that is the focus from Dr. Mims' laboratory since 2006 to see the reuse of this technology. So can fish survive in this water? Can they eat the Daphnia? So we use these 8 experimental tanks and stock them with 1,500 larvae of paddlefish and feed them with the Daphnia that was collected from the secondary clarification tank. And also we use other decommissioned tanks. This is, for example, a sludge thickener tank, and we stock with 15,000 paddlefish larvae. And this is the Daphnia that was collected. So we feed them twice a day. It's depending on the production, and that's going to depending on the production of the Daphnia in the clarifier, it's going to depend on the survival. But what we found out is, on average, we can have around 57% survival and around 11 grams. But the next question is, does this fish has any kind of contaminants that could have any concern for the humans? So we analyzed for 38 contaminants, and we just found 8 contaminants on this fish. And all the values were well below the FDA action level. As we can see in this column, there is contaminants for the Daphnia. This is the reclaimed water, fish raised in reclaimed water, and the ones we have a control, which were paddlefish that were raised in city water, but they were on Daphnia. So the source of the contaminants were coming from the Daphnia, although they did not bioaccumulate, as we can see here. This was a 30 days grow-out period for phase 1 paddlefish. So the next is to produce a phase 2 paddlefish. In order to produce a phase 2 paddlefish, we decide to use decommissioned digester tanks, which is roughly 1,000 cubic meters, and stock them with 50,000 phase 2 paddlefish. We decided to treat these 2 tanks, one as a static system where no reclaimed water was exchanged, and the other one as a flow-through system where there was 280 liters per minute of reclaimed water flowing into this tank. We fed the paddlefish 5% of the body weight, and we grow them for 120 days. The results, flow-through system did better. By better, I mean higher survival. Fish were larger. The feed conversion ratio was better, and this was due probably for the water quality, because in the static system our nitrates were really high. In fact, we have to add salt to those systems to avoid brown blood disease. What about the contaminants on this phase 2 paddlefish? Well, all the values were well below FDA action levels, which means they are safe to eat, although a phase 2 is probably too small to eat. But we have mercury, and we see the FDA action level is 1, and we can see either in the static or flow through, all the values were safe. Probably total chlorine was a little bit higher than the static system, but it's still lower than the FDA action level. So what we learned from this project is that, yes, we can use reclaimed water, which is a secondary disinfected water for paddlefish production. We can easily reuse the decommission facilities, and that doesn't require a lot of capital. So you can start a business with little capital. Flow-through systems did better survival and growth than the static system. We can use this system as a zero discharge system because most of the decommissioned old wastewater treatment facilities are built next to the new facility, so we can retrofit the water that is used in aquaculture back to the treatment process. We can easily use the Daphnia collected from the cryofied tanks. So far, we were able to produce food safe as a stocker fish, but future research needs to be done to produce into a market size and verify that the fish are still safe to eat. That was it. Thank you.